I considered that, okay, we are now having a network that can map XYZ to a distance, so a geometric property. Can I use this for predicting this thickness, thinning, or deviation of the object? And it worked.
Hello and welcome to the AI Master Group podcast, featuring the people who are building the future of AI in their work today. I'm your host, Jim Griffin. Today, I am very happy to have as my guest Aida Farahani, who is a PhD candidate with a focus on 3D deep learning. She's doing research related to implicit fields at the Technical University Chemnitz, Technische Universität Chemnitz. Tell me later after the microphone is off how I did on that pronunciation. Aida, welcome.
Hi, thanks for inviting me.
It's great to have you. You know, the university you selected has a solid reputation in the field of machine learning and AI. Can you tell me a little bit about your journey there so far, your work and your studies leading up to today?
Yeah, so my name is Aida. I'm from Iran, where I grew up and went to school. I found my passion for programming during high school, like many people, and I was fascinated by how code could bring ideas to life and creativity. I completed my bachelor's in software engineering and continued my master's in mechatronics engineering, focusing on robotics and AI. And after gaining some experience in field of research and working in some research institutes and also teaching at university, I decided to pursue a PhD in AI in Germany. And here I am. And my main focus is now machine learning and 3D data, which is really high trend nowadays, and you hear about it a lot, I would say.
We sure do. And however, there's some things that you're working on that we don't hear as much about because they're sort of on the cutting edge. We know from the introduction that I gave just now that you're working in the field of 3D deep learning with a research that focuses on implicit fields. Can you describe what those are and how implicit fields are different from traditional approaches and why they're a promising direction for research today?
Sure. Implicit fields are not new in computer graphics, so they have been for years there, but the combination of them with neural network is something new. So what implicit fields are? Basically, you could imagine a 3D object and you consider, for example, the points that have 1 centimeter distance from the surface. All the points with the same distance would create a field around the object, and they are belonging to one field. And now you can imagine how you can extend these fields, like you can imagine any distance from the surface and you could have a lot of, I would say, infinitive number of fields around the object and also inside. So this is basically the way that implicit fields define the objects. And as you can see, it's very different from structures like meshes or point clouds that explicitly defined the object. And for representing these implicit fields, you need some mathematics. For example, the famous one, sine distance function, which is a function that receives a point and returns you the distance from the surface of the object. And whether you're inside or outside, the sign of this distance would differ. And obviously, when you are on the surface, you have the zero distance. So this is the basic difference that we have with traditional methods like mesh or point cloud or other explicit methods.
Very interesting. I think, correct me if I'm wrong, a pretty important reference for this area of research that you're in right now is what's referred to in a colloquial way as the DeepSDF paper, which stands for Deep Signed Distance Functions for Shape Representation. Can you summarize the key contributions of that paper?
So, first of all, the main advantage of these implicit fields is that they can be easily integrated with neural networks. And this is the key contribution of this DeepSDF paper that the authors have been proposed in 2019. And since then, they got a lot of citations. So and every day also it continues up to now. The The main advantage is that, so first of all, you have a continuous representation. You can imagine when you have a complicated 3D surface with fine details and curvatures, if you want to introduce it with meshes, you need to increase the size of your mesh, the size of vertices, the edges, and basically you would have a lot of memory and afterwards computations. But what happens in this implicit field, as you face with a continuous field and so continuous space, you could get rid of all limitations you have before, and you are able to represent the higher resolution of the 3D very easily. And this was the first time that neural networks have been integrated with implicit fields, and they presented DeepSDF as a deep neural network plus sign distance function. And as you know, so neural networks are very powerful function estimators. So when you have sign distance functions in computer graphics and you have neural networks as function estimators, and when you put them together, then you're able to embed the 3D shapes inside your neural network. And this could give you a lot of flexibility and power in computation.
Well, you said something just now that using this technique, you're able to do it very easily. Maybe easy for you. Anyway, I know that one thing that you've done that is pretty interesting is that you've developed a new method to predict the deformation of 3D objects as a result of surface forces. Can you tell us more about that?
Sure. When I say easy, I mean easy compared with what we have with meshes. For example, when you work with meshes and neural network, you have to bring the whole object all at once to the network, which means if you have a large mesh, then you would have a lot of neurons in your input layer to just present it, and then you have your subsequent layers, and it will make your network so large. And if you have a large network, not only you have a huge amount of computation, but also you need a lot more data to be able to represent your objects with this lot of parameters. And what we have in implicit fields, we replace these data units instead of the whole shape with this just individual coordinates points in the space. So the input of the network is the XYZ coordinate of the arbitrary points, and you return the SDF value in the end. So the network would be smaller, you would have very less amount of parameters for training your network, and you have fast process.
You're listening to the AI Master Group podcast.
So the network would be smaller, you would have very less amount of parameters for training your network, and you have fast process. That's why I say it's easier. And of course there are some issues and challenges, which I also had as well. So yes, as you mentioned, these type of algorithms have more application in field of computer graphics, and that was one of my challenges, so that I could not really have a reference to even compare my results with. However, I saw a potential in this DeepSDF, which is defined for classes of objects and embedding the 3Ds, to extend it to represent the deformation. So what we have in our project was a deformation of 3D shapes, I would say. I mean, I will explain what they are, but for the start, so we have the problem of deformation of objects. So we have some forces as vectors that apply on a 3D object and deforms it. And we wanted to predict how they are related. As I said, the neural network as a function can perform this well, and when you use implicit fields for representing your 3D, then you'll be able to map these force and corresponding deformation in the end. So that's why, and that's how I applied this algorithm in my case. On the other hand, DeepSDF focuses on 3D objects that have volume, or called watertight. So one great aspect of these watertight meshes is that they have the inside-outside region. That's why we have these plus or minus signed distances. And however, in our research, the data we had, or the simulation data we had, were the shell meshes. So shell meshes, you could imagine as a metal blanks. So, for example, when you in industry, you want to produce some part for your car, the door or everything. So you could imagine a shell mesh, which is a blank metal, and it needs to be deformed to your desired shape. So there we didn't have any inside-outside region, so we could not directly apply DeepSDF, but I considered that, okay, we are now having a network that can map XYZ to a distance, so a geometric property. Can I use this for predicting this thickness, thinning, or deviation of the object? And it worked. So yes, first I need to prepare data so that we can feed it to our DeepSDF network, and then after training you were able to predict the thickness, thinning, and deviation of the points so accurately and reasonably fast. Yeah, and you solve the problem.
Wow. So you said reasonably fast. What kinds of speeds have you achieved in your work so far?
Yeah, in our example, so there was typically an expert, a mechanical engineer, design the environment, create the geometry, do the meshing, and add the constraints, and execute the simulation. This would take up to about 20 minutes in our case. And what we did, so you could reduce the time into a few seconds for the prediction. And you could see it could save a lot and could be of interest of the experts, that they can save a lot of time and even money. So that sounds good.
Yeah, that's interesting. So it's interesting. You made the point just now that you're talking about deformation of shapes. Maybe it thins because it's being molded into being a door or a car or something like that. So this is very interesting to me because more commonly when we're talking about deformation of shapes, it's in the context of computer graphics, maybe an animation or something like that. But your primary use case is mechanical engineering. And so can you tell me a little bit more about that domain and what's going on in that domain, mechanical engineering, and the intersection of your work to that?
Yeah, so as I mentioned, this deformations were of interest in this mechanical processes. So I think it has a good potential in industry. So okay, I cannot say that we would replace FEM simulations because we still need them and they're powerful methods. And even we use the FEM simulations to train our neural networks. So basically provide the data for the networks. But it gives you flexibility to, instead of executing the simulations from the beginning, so what is typically done is that the expert needs to manually adjust the parameters. So you run the simulation, you look at the results, and then you decide based on your expertise in which direction you should go and how you should adjust the parameters, and then you re-execute the process again, which means a lot of time and energy. But when you train your network with enough amount of data, and this network can give you the results just in a few seconds, because it is working in a continuous space and it already learns about this mapping between this input force or even more parameters and the corresponding physical property. And this is the power of machine learning that can find these maps between these two domains and connect them to each other. And maybe I should mention an important thing here. In the project, we had another issue. So we had a few number of samples. So for example, 1,000 meshes, I would say, which looks not enough for training a neural network. When we talk about neural network training, we mostly talk about thousands or even millions of data units. But here, when we use implicit fields, we are able to not only use a limited amount of meshes, but also if they are so large. So if you increase the size of your mesh, then you would, as I mentioned, you would need a larger network. But if you use the implicit fields, you can also handle very large meshes, very complicated ones, because you are basically solving your problem in a continuous field. And this could be also a very impressive advantage of this type of methods.
I can imagine. Yeah. So you said a bit ago, if you have enough data, and you were mentioning about that again. So how much data actually do you need in order to do these simulations? How do the simulations work exactly?
Yeah, so basically for the neural network, for example, if you want to train on images, image is the unit of your data and you need a lot of them. But in implicit fields, you basically change the idea from this units of data from the whole object. You just focus on these points. So because we just consider, okay, we have a bunch of points and we want to know how is our distance from the surface. And this is the way that we define our object. So we reduce the problem from these units, from these 3D objects to these points, and then, as I mentioned, you can even have large meshes with a few number of samples, which is really, I think, important for side of mechanical engineers also, because even producing the simulations is not so easy. So you would rather have less samples for your training, and yeah, so that would be the difference. Yeah.
Very interesting. So I'm curious to know, how is your PhD dissertation coming along?
Well, I'm kind of in the final stages of writing, and I hope I can finish it soon. So I'm really interested to see how it's going. Yeah. So
I see. You're in the final stretch.
Yes.
Hopefully so, right? So this has been great, Aida. I'm so grateful. If people are interested in following up on your work, how can they get in touch with you?
Well, it's always a pleasure to talk to the people with the same viewpoints and having issues in similar things, and we can discuss. So I really enjoy networking people. Yeah, and I think so. LinkedIn would be a great option to connect. So I'm available there, and yeah, looking much forward to talk to the people they are interested in the field. Great.
Oh, that's very nice of you. Well, once again, Ida, I'm so grateful for this opportunity to learn more about your work, which is really advancing the field. More power to you. Finish that dissertation. Let me know when you get that thing published. I want to read it.
Thank you. Thank you so much. And thank you for having this opportunity, providing this opportunity for us. Thank you so much.
You've been listening to the AI Master Group Podcast. I'm your host, Jim Griffin. Until next time, stay curious and stay in front.